Before touching any of these questions, let's picture the general shape of every single one. You're given a vector field, an arrow at every point in space, and a curve, a path someone walks along. The question always asks the same thing. How much does the field push along that path, start to finish? And the pattern to recognize is that no matter how messy the field or curve looks, the method never changes. Parametrize, differentiate, dot product, integrate. Question 1. Straightforward line integrals. 5 different fields, 5 different curves, but the pattern to recognize is this. Whenever the curve is already given as r of t, you can skip parametrizing. You're handed it for free, so go straight to finding r prime of t. Part A. Evaluate the line integral of f dot dr, where f of x, y equals x squared y, xy cubed, and C is the curve r of t equals t cubed, root t, for t between 0 and 1. Step 1. Substitute the curve's components into the field. Step 2. Differentiate the curve to find r prime of t, giving 3t squared, 1 over 2 root t. Step 3. Dot the two vectors together. This gives 3t to the power 8.5 plus 0.5t to the 4. Step 4. Integrate this over t from 0 to 1. The answer is 79 over 190, approximately 0.416. Part B. Evaluate the line integral of f dot dr, where f of x, y equals the square root of 2xy, sine of y, and C is the parabola, y equals 2x squared, from x equals 0 to x equals 1. Pattern to recognize. When a curve is given as y in terms of x, not as r of t, let x itself be the parameter, so set x equal to t and y equals 2t squared. Differentiate both components with respect to t, substitute into the field, then dot the two vectors and integrate from 0 to 1. The answer is 9/5 minus cosine of 2, approximately 2.216. Part C. Evaluate the line integral of f dot dr, where f of x, y, z equals cosine x, xz, sine z, and C is r of t equals t squared, 2t, t cubed for t between 0 and 1. Same method, substitute, differentiate, dot, integrate. Watch carefully for the z component interacting with x in the field. That's a common point where terms get mixed up. The answer is 4/3, minus cosine of 1 plus sine of 1, approximately 1.635. Part D. Evaluate the line integral of f dot dr, where f of xy equals x squared y, y cubed, and C is r of t equals cosine t, sine t, for t between 0 and pi over 2, a quarter circle. Pattern to recognize cosine and sine parametrization. Always expect trigonometric identities to simplify things once you multiply everything out. The answer is 1/4 minus pi over 16, approximately 0.0537. Part E. Evaluate the line integral of f dot dr, where f of xy equals e to the 2x x squared y, and C is r of t equals t squared negative t cubed for t between 0 and 1. Same method throughout. This one is mostly a differentiation and algebra workout with no special trick. The answer is e squared over 2 minus 1/5, approximately 3.495. Question 2. Find the potential field first. Pattern to recognize. Whenever a question hands you a potential function directly or asks you to find one, this is a strong hint the field is conservative, meaning you should use the fundamental theorem for line integrals, not a full parametrized integral. The general method here has 4 steps. Step 1. Test the field using curl. If curl equals 0, proceed. Step 2. Integrate each partial derivative equation separately, one variable at a time. Step 3. Compare all resulting expressions and match up the missing pieces to find f. Step 4. Once you have f, skip the full line integral entirely. Just evaluate f at the end point, then subtract f at the starting point. Part A. Given the potential f of x, y equals y times e to the 2x, so the field is 2y e to the 2x, e to the 2x, evaluate the line integral of f dot dr along the upper semicircle of radius 1 centered at the origin from -1, 0 to 1, 0. Pattern to recognize. For conservative fields, the actual shape of the curve becomes irrelevant, only the start and end points matter. The answer is 0. Both endpoints sit on the x-axis where y is 0, so despite the long curved path, the shortcut collapses it to a single line. Part B. Given the potential f of x, y equals x cubed y cubed, so the field is 3x squared y cubed, 3x cubed y squared, evaluate the line integral of f dot dr along any curve from 0, 0 to 1, 1. The answer is 1. Part C. Given the potential f of x, y equals root x plus root y, so the field is 1 over 2 root x, 1 over 2 root y, evaluate the line integral of f dot dr from 1, 1 to 4, 9. The answer is 3. Part D. Given the potential f of x, y equals x, y, z, so the field is y, z, x, z, x, y, evaluate the line integral of f dot dr from 0, 0, 0 to 1, 2, 3. The answer is 6. Part E. Given the potential f of x, y equals e to the x sine y, so the field is e to the x sine y, e to the x cosine y, evaluate the line integral of f dot dr from 0, 0 to 1, pi over 2. The answer is E, approximately 2.718. Question 3. Path independence built from the fundamental theorem. This time you're given the landscape itself, f of x, y equals x squared plus y directly, not the field. Pattern to recognize. Since f is already known, the gradient field is automatically conservative, so the fundamental theorem says the line integral only depends on the start and end points, not the path shape at all. Part A. Find 2 points where f jumps by exactly 2, and state the value of the line integral between them. Step 1. Pick any 2 points. Step 2. Evaluate f at both. Step 3. Subtract, and adjust your chosen points until the difference equals exactly 2. Answer. From 0, 0 to 1, 1, f goes from 0 to 2, so the integral is 2. Part B. Find 2 points where f gives exactly 0, and state the value of the line integral between them. Pattern to recognize. The easiest way to guarantee 0 is picking a start point and an end point where f takes the exact same value, even if the points themselves are different. Answer. From 2, 0 to 0, 4, f equals 4 at both points, so the integral is 0. Question 4. Conservative but not path independent. A deliberate trap. The field is f equals negative y over x squared plus y squared, x over x squared plus y squared. This field swirls around the origin, but the origin itself is a hole. The field isn't even defined there. Pattern to recognize. This is exactly the situation where the standard theorem breaks. Step 1. Compute the curl directly. It equals 0 everywhere the field is defined away from the origin. Step 2. Choose the unit circle as a closed loop around the origin. The loop integral works out to 2 pi, not 0. Step 3. Explain why this doesn't contradict the earlier theorems. Those theorems require the field to be defined and smooth across the entire plane, not just almost everywhere, and here there's a hole right at the origin. Question 5. Closed loops. Choose your own method. Every part here is a closed loop, so Green's theorem is now available as a shortcut, alongside direct parametrization. Pattern to recognize. Whenever a closed loop bounds a simple region, always ask first, would Green's theorem be faster here than 4 separate line integral calculations? Usually, yes. Part A. With p equals y and q equals x squared, evaluate the closed loop integral of p dx plus q dy around the triangle with corners 0.0, then 1.0, then 0.1. Step 1. Decide whether to split the triangle into 3 straight line segments or apply Green's theorem directly. Step 2. Find curly dq by curly dx minus curly dp by curly dy, which gives 2x minus 1. Step 3. Set up the double integral over the triangular region, being careful with the slanted boundary. The answer is negative 1/6. Part B. With p equals negative y and q equals x, evaluate the closed loop integral of p dx plus q dy around the unit circle. Pattern to recognize. Circular boundary. Polar coordinates are almost always the fastest route once Green's theorem converts this to a double integral. Here curly dq by curly dx minus curly dp by curly dy equals 2, so the integral is just twice the area of the unit disk. The answer is 2 pi. Part C, with p equals 0 and q equals x squared, evaluate the closed loop integral of p dx plus q dy around the rectangle with corners 0.0 and 2,3. Pattern to recognize, rectangular boundary. Green's theorem turns this into a simple double integral with straightforward limits. Here the derivative expression is 2. The answer is 12. Part D, with p equals xy plus sine of x plus y and q equals x squared plus sine of x plus y, evaluate the closed loop integral of p dx plus q dy around the triangle with corners 0.0, then 2.0, then 0.2. Step 1. Apply Green's theorem regardless of how messy p and q look. Step 2. The sine terms cancel exactly when you subtract, because sine of x plus y has the same partial derivative in x as it does in y, leaving just x. Step 3. Set up the double integral using the triangle's actual boundary lines as limits. The answer is 4/3. Finally, proving Green's theorem, building it from scratch. Instead of using Green's theorem, we're now proving why it's even true, starting from the simplest possible region, a plane rectangle. Question A. Why splitting into two equations is enough? The full theorem statement has curly dq by curly dx minus curly dp by curly dy, all in one expression. Pattern to recognize, if you can prove each piece separately, one for p, one for q, then simply subtracting the two proven results gives you the whole theorem for free. Question B, the rectangle case. Step 1, walk the rectangle's boundary. Right along the bottom, up the right side, left along the top, down the left side. Step 2, notice the vertical sides contribute nothing to the p dx integral, since dx is 0 along them. Step 3, the only surviving contributions come from the bottom and top edges, travelling in opposite directions. Step 4, show this matches exactly what you get from integrating curly dp by curly dy over the rectangle, using the fundamental theorem of calculus in reverse. Step 5, repeat the same logic for the q dy integral, using the left and right edges instead. Question C, extending to a region with curved top and bottom. Pattern to recognize, the exact same cancellation argument works even when the top and bottom of the region are curves instead of straight lines. You just replace fixed y values with functions of x. Question D, extending to fully general regions. Step 1, argue that any region expressible both ways, bounded left-right by functions of y, and bounded top-bottom by functions of x, can have both halves of Green's theorem proven using the same rectangle-style argument, just with variable limits instead of fixed ones. Step 2, conclude that since most regions of interest can be described this way, or split into pieces that can, Green's theorem holds generally, using exactly the same cancellation at shared edges idea.